Good morning, everyone. Today we'll be taking our lesson to Africa. Up to this point, we have discussed genetics quite extensively and wanted to provide us with an evolutionary phenomena thousands of years in the making. Before we get started on our journey for survival, I want to introduce you to some key players. First up is our normal hemoglobin, or red blood cell. It is made up of 4 protein units and iron molecules which aid in the transportation of oxygen. A common misconception is that most people believe red blood cells to be real cells, when in fact they are not. In order to be considered a cell, you must contain genetic information, either free-floating or enclosed within a nucleus. Next up, we have mutated hemoglobin. You can see based on the picture that the genetic mutation, specifically a base substitution, causes sickling of the red blood cell when exposed to low levels of oxygen. Due to their sickle shape, they can often get caught within the capillaries of the body, leading to major bodily complications. Lastly, the driving force behind our story, malaria. Most people associate malaria with mosquitoes, but are unaware that the mosquito is simply acting as a vector for the malaria. We will discuss more about vectors shortly, but before, let's take a closer examination. Malaria is a unicellular plasmodium from the kingdom Protista. From the diagram, we can see a nucleus present, indicating that malaria would be classified as a eukaryotic cell. So we might be asking ourselves at this point, how does a plasmodium and a genetic mutation get twisted in this evolutionary crossroad? As I mentioned earlier, let's take our adventure to Africa. On the right, we see Africa color-coded to depict the areas most affected by malaria. On the left, we see Africa color-coded to depict the allele frequency of sickle cell. The allele frequency is how often a particular genetic trait is expressed within a population. As we can see, the color coding for malaria and sickle cell overlap tremendously. But why? To understand how they are evolutionary related, we must first better understand our major selective force, malaria. From the diagram, we see that the mosquito is acting as a vector. A vector is any organism used to transport a pathogen. A pathogen is any microorganism that can cause a disease. In this case, the mosquito is being used to transport the plasmodium from human to human when the mosquito bites you, allowing the plasmodium to enter into the body's bloodstream. An uninfected mosquito is able to become a new vector if the human attacked was infected with the plasmodium, thus continuing the spread of the infection. To better understand how a genetic mutation could become a survival advantage, we must comprehend Darwin's theory of evolution. Charles Darwin suggested that within a population, mutations would create variations. Some of the mutations would be favorable enough, allowing the survival and reproduction of those organisms, while organisms expressing an unfavorable mutation would reproduce in lower amounts until those alleles were removed from the gene pool after multiple generations. The picture below is simply another illustration of Darwin's theory of evolution. Natural selection is dependent on variation, and variations are deemed favorable or unfavorable based on how they ensure survival against varying environmental pressures. Now that we have a general overview of natural selection, let's dive deeper into the genetics of sickle cell. The diagram below depicts a family whose parents are both heterozygous, AS, where the A allele codes for normal hemoglobin, while the S allele codes for sickle cell hemoglobin. AS individuals display a codominant trait, meaning that their body expresses both the A normal hemoglobin and S sickle cell. We can see that based on the 4 offspring, one child is completely free of the sickle cell, while 2 siblings are carrier for the sickle cell allele, with the last child having 2 copies of the S allele, thus resulting in the child developing sickle cell anemia. Individuals diagnosed with sickle cell anemia often do not live long enough to reproduce due to various bodily complications caused by the sickle-shaped hemoglobin. Before we move forward, let's stop and ponder. We notice from the maps of Africa that the allele frequency of sickle cell overlapped with the malarial infection. But if SS individuals die prior to passing on their genes, how is the S allele being maintained at such high frequencies in the population? Let's focus on the diagram to the left. We can see that in the presence of low oxygen, the normal hemoglobin does not sickle. Yet we can see that from the bottom of the image, in the presence of low oxygen, hemoglobin will stick together to form a rod. These rods come together to form a cable, which kinks the red blood cell into a rigid sickle shape. Why is this phenomena critical to the survival of individuals in areas of high malarial infection? To answer that, let's take a look at the graphic to the right. As you can see, individuals who are AA have a strong affinity to the plasmodium, allowing for the infection to increase at faster rates with no way of reducing the malarial infection. However, individuals who are AS express both types of hemoglobin. So when the plasmodium enters into the red blood cell, a side effect of the malarial infection is increased oxygenation consumption within the cell. The increased consumption of oxygen by the plasmodium causes the red blood cell to sickle, causing a weak bonding affinity. This weak bonding affinity allows for it to be more easily uptaken by the macrophages free floating within your blood. As a result, the individual is able to maintain normal bodily functions due to the normal hemoglobin, while decreasing the malarial infection due to the sickled hemoglobin being eliminated faster by the body. These findings discussed were made possible by 3 distinct studies ran by Dr. Allison. In his first study, he studied 15 individuals with AS genotype and 15 other individuals with the AA genotype. What he found was that 14 out of 15 people who had the AA genotype developed malaria, while only 1 individual with the AS developed it. In his second study, he tested close to 300 children and found that 28% of the children with the S allele developed malaria, while 46% of the children without a sickle cell trait developed the disease. In his third study, he took samples of over 5,000 people all over Africa and found that in the areas where the plasmodium was present in high prevalence, so was the sickle cell allele. In this particular environmental situation, the S allele is viewed as being advantageous and thus is passed on to the next generation. But if the S allele infection in an environment The findings discussed were made possible by 3 distinct studies ran by Dr. Allison. In his first study, he studied 15 individuals with the AS genotype and 15 individuals with the AA. What he found was that 14 out of 15 people who had the AA genotype developed malaria, while only 1 individual with the AS did. In his second study, he tested close to 300 children and found that 28% of children with an S allele developed malaria, while 46% of children without a sickle cell trait developed the disease. In his third study, he took samples of over 5,000 people all over Africa and found that in the areas where the plasmodium was present, so was a high prevalence of the S allele and vice versa. In this particular environmental situation, the S allele is viewed as being advantageous and thus is passed on to the next generation. But if the S allele was in an environment in which the possibility of a malarial infection was low, then the S allele would no longer have its survival advantage and now would be considered a disadvantageous trait in the population. Applying your knowledge of genetics and what we just discussed, which family would you suggest has the most advantageous traits for survival in the middle of Africa and why? And the next question, would the same family have the same survival advantage if they were to be living in the United States?